All right, next focus question. Factors that affect equilibrium. All right. Now, this second focus question is asking you to apply Le Chatelier's principle. All right, I can tell we're happy to be together, though we may not be that happy doing chemistry. Le Chatelier's principle states that when a system at equilibrium is changed or subjected to some kind of a pressure, the system will respond in order to minimize the change. All right, now, in order to solve Le Chatelier's principle, we use ICE tables, right? Where we identify the initial conditions that's I. We identify the change in the system, that's C. And I also think that it's helpful if you identify the opposing change. All right, and then the last bit, when the opposing change has taken place, we will end up with a new equilibrium. So, in order to apply Le Chatelier's principle, we need to think about the different ways in which a system can be changed. All right, we can increase the concentration of a reactant. So if we increase the concentration of a reactant, what's the opposing change? All right, so if we've increased the concentration of any of the reactants, the opposing change will be to use up the added material. So this will favour the forward reaction. Now, when you come to answer questions about Le Chatelier's principle, you need to put it in terms of the reaction that you're given. So don't just say favour the forward reaction. If we're talking about, say, the cobalt complex going to cobalt chloride, if we increase the amount of water in the solution, it's going to turn from blue to pink. The reason is because the water is being absorbed into the complex ion, so it's using up the extra water. So you look at your reaction and you see if we're adding this, the reaction is going to move in the opposite direction. So the result will be fewer cobalt COCl4 ions and more COH2O6 ions. All right. Now, I'm only doing one. There's 4 possible ways that we can change concentration. We can increase a reactant or we could decrease a reactant. I'm only writing one of those up here because I'm assuming that you can extrapolate in your brain. All right, so if we increase the reactant, the opposing change is to use up the reactant. But what if we decrease the reactant? We take one of the reactants away. The opposing change will be to produce more of that reactant, so the reverse reaction will be favoured. Then we could change the concentration of a product. So if we increase a product, the reaction will move in the reverse direction to use up the additional product. And if we take away the product, that will favour the forward reaction, which produces more product. All right, so I'm giving you one example of a change, but there are 3 other ways in which you can change concentration. Right, the second thing that we can change is a change in pressure. All right, so if we increase the pressure, what will the system do? All right, so if we increase the pressure, the opposing change is to decrease the pressure. Now, a system can only alter the pressure if there are an uneven number of moles of gas. If you've got the same number of moles of gas on both sides of the equilibrium, the system is insensitive to pressure. In other words, it doesn't matter whether the pressure goes up or down, the reaction can't do anything about it. But if you've got fewer moles of gas on one side and more on the other, if you increase the pressure, the system will move in the direction that has fewer moles of gas because that reduces the number of particles in the volume, therefore it reduces the pressure. Right, so this favours the side with fewer moles of gas. Okay. Now, increasing temperature is different to increasing concentration and pressure because when we increase the temperature, we actually change the position of the equilibrium. Right? So the equilibrium constant changes. The ratio of products to reactants changes. But changing the temperature also alters the rate of the reaction. But when we're applying Le Chatelier's principle, we have to consider an increase in temperature is adding heat. Right, so when the temperature goes up, we are putting more heat into the system. So what's the opposing change? It will favour the reaction that uses up heat. So which one will that be? So remember that in a equilibrium system, the forward reaction and the reverse reaction, one will be endothermic, the other will be exothermic, and the change in enthalpy will be the same numerically, but different in sign. All right, so if the forward reaction is exothermic, giving out energy, then the reverse reaction will be endothermic, using up, and the amount will be exactly the same. So these are the three possible changes. Now the syllabus then gives us three examples. So the first system, a change in temperature, is the cobalt equilibrium. All right. I almost gave you the wrong information there. So the first example is changes in temperature. So the example they give you is the cobalt equilibrium. Now, if we have pink crystals of cobalt chloride, so it's got water molecules attached to it, and we heat that strongly in over a Bunsen burner, what happens to the crystals? They turn from pink to blue. So they lose water. Now, because we're heating them, we're adding heat. So it favours the endothermic reaction. So the change from pink to blue tells us that this forward reaction is an endothermic reaction. So we heat them up and the cobalt chloride crystals lose water and turn from pink to blue. If we cool them down, if we take heat away from the system, it will try to generate extra heat to replace the energy that we took away. So that means that it will go from blue to pink. So you have to be able to explain changes in temperature with this reaction. All right. Now, for changes in pressure, the system, the reaction that we're required to know is the dinitrogen tetroxide. All right, now tell me about this system. What colour is this gas, dinitrogen tetroxide? Right, dinitrogen tetroxide is colourless. Nitrogen dioxide is brown. So what will happen if we increase the pressure? What happens to the colour? So if we've got this in a syringe and we push the plunger of our syringe in, so we increase the pressure, what will happen to the colour of the gas? Will it go darker or lighter? Okay, what I'm hearing is right, if an increase in pressure, right, look over here. If we increase the pressure, the system will try to decrease the pressure. So it favours the side with fewer moles of gas. So in other words, the reaction will go in reverse. Now, it's not just enough for you to identify the change, you also have to be able to explain the change. Right? You have to explain why does the number of moles vary the pressure. So you've got to be able to talk in terms of the number of particles in a given volume determines the pressure. The more particles in the volume, the higher the pressure. So if you increase the number of moles, that will make pressure go up. If you decrease the number of moles of gas, that will make the pressure go down. Any questions about that? All right, now, for changes in concentration, now here, Year 12, you have to remember that we did experiments with these three reactions. And so you could be asked about the practical that you did with the cobalt chloride, with the dinitrogen tetroxide, or with the iron and thiocyanate. So with this particular reaction, what happens if we increase the amount of Fe3+? So if we add more Fe3+, what will happen to the colour of the system? Right, it will go from a light red to a much darker red because the extra Fe3+ ions will react with the additional thiocyanate ions and make more of the complex ion. Now, the last bit of this focus question asks you to relate equilibrium changes to collision theory. All right, so we've got collision theory and equilibrium. So you could be asked to explain any of these changes in terms of the collision of particles. All right? So if you increase the concentrations of the reactants, right, so you have more reactants, what will that do to the rate of the forward reaction? So if you're increasing the rate of the forward reaction because you've got more particles, remember rate is proportional to the concentration of the particles. So you have more reactant particles, that will make the rate of the forward reaction faster. So what that means is that you now have a rate that looks like this. You've got a lot of forward reaction and not much reverse reaction. Now, what's going to happen to the number of the amount of product particles? What will happen? It will increase. So as you increase the number of product particles, what will happen to the rate of the reverse reaction? If you increase the concentration of product particles, that will increase the rate of the reverse reaction because you have more product, right? And as the forward reaction is proceeding at a high rate, what happens to the amount of reactant? It decreases. So what happens to the rate of the forward reaction? It slows down. So when we add the reactant, the forward reaction is initially faster. That makes more product. So then the product reaction increases its rate. So what happens is that the initial high rate of the forward reaction, low rate of the reverse reaction, and then as the amount of product, as the amount of reactant decreases, this comes down. And as the amount of product increases, this comes up, and they meet in the middle. And when they meet in the middle, the rate of the forward reaction and the rate of the reverse reaction is equal, and so it's back in equilibrium. Right, so that's how you explain equilibrium changes in terms of collision theory. Okay, so rate of the forward reaction increases. All right, so now you may not be asked what happens if you increase reactants. You might be asked about pressure, or you might be asked about temperature, but you have to be able to explain the change in equilibrium in terms of the temperature effect, right? That's on the using up energy. In terms of the pressure effect, that's about how closely packed the particles are together, or in terms of concentration, which is also about how closely packed together they are.